Okay, so electron configurations can be SPDF notation, they can be orbital diagrams, or they can be what we call quantum numbers. So a quantum number is like an address system for the electrons, right? So Bohr introduced he was the first to introduce the quantum number, right? And so the quantum number, the first quantum number, is essentially the energy level. But now we've broken it down and we have four specific quantum numbers. And every electron has four quantum numbers. And of course, each of those numbers varies. So we'll go in order from the beginning. The first quantum number is called the principal, and the range can be anywhere from 1 to infinity. All right, so for example, when I say the principal quantum number 2, that means energy level 2, or energy level 3, or 4, or 5, 6, 7. You're not going to see principal quantum numbers higher than 7 because there's no element with 8 energy levels that's known. Okay, so technically, mathematically, it goes up through infinity, but really it's 1, 2, 3, 4, 5, 6, or 7. Okay? All right. The secondary quantum number has to do with the sublevels. And you know the sublevels, S, P, D, F, are the only ones that are actually in use. Hypothetically, there's G and H, right? But they are coded as S has a secondary quantum number of 0, P is 1, D is 2, F is 3. Right? They're number coded. Now, to understand, the range is anywhere from 0 through n minus 1, meaning the first secondary quantum number is 0, and then the second one will be 1, the third one is 2, the fourth one is 3, and so that's why they're designated to the SPDFs that way. Okay, so secondary quantum number, this means sublevel type. Whereas this is energy level. Okay. The third quantum number is what we call the magnetic quantum number. And this has to do with the orbitals. And this is another reason why we have to learn how to draw the orbitals. So the orbitals are actually designated with numerical codes. So for example, if I have an electron like in, let's say this is 3p3, all right? These orbitals are specifically numbered, and however many orbitals there are, the middle is always designated with 0. Any orbitals to the left of 0 are negative, so this guy here would be called -1. Any orbitals to the right of 0 are positive, so this is going to be +1. Each of those 3 orbitals then can now be identified specifically. If there was a d subshell with 5 orbitals, the same rules apply. The middle is designated as 0. The left are the negative numbers, so they look like this. And the right are positive, so they look like this. And of course, if there was an F, then you would have 7 circles, 7 orbitals, and the range would be -3 through +3. So, the values of M sub L, because that's how we, you know what, that rhymes. I didn't even tell you the symbols. So, principal quantum number is N. N. The secondary is L. The third, M sub L. Okay. And the range, -L through +L. So let me elaborate on that. This subshell right here is what type? It's a p-type. What numerical code is given for the secondary quantum number for a p-type? Less than that. This guy right here, 1, right? So when I say the range of the quantum number, the magnetic quantum number, is negative L through positive L. Well, if L was 1, then your range is -1 through +1. Here, this is a D, right? D has a secondary quantum number value of 2. So the magnetic range is going to be -2 through +2. Okay, those are the hard ones. The last one's easy. M sub S, this is what we call the spin, magnetic spin. And this quantum number has only 2 possible values, positive half or negative half, that's it. And it's pretty easy because the positive half is the up arrow and the negative half is the down arrow. So depending on which one it is, that's the value we give, positive half or negative half. Okay, so this makes more sense if we just start pulling examples. Okay, so hydrogen. Hydrogen looks like this. Right? 1s1. Principal quantum number, N, is right here. It's energy level 1. Secondary quantum number is the fact that this is an S, and remember that S is coded to be 0. Magnetic quantum number is which orbital is it in the set? Well, in an S sublevel, there is only one orbital, and if there's only one orbital, it must be the 0 value, the middle. And then the last, the magnetic spin, is it up or down? It's up. So the quantum numbers would be written as 1, 0, 0, +1/2. Okay, let's do one for fluorine. So fluorine looks like this. By default, when we ask about quantum numbers, what we're really referring to is the last the last electron added. So in fluorine's case, 2p5. Everyone see I made it black. That's the last electron that was added. Okay. So what is the primary quantum number? In other words, what's the energy level we're talking about? 2. What sublevel are we in? P. And P is coded to be what number? 1. Which orbital orientation are we in? The 0, the middle. The middle is 0, right? Because this is 0, this would be +1, this would be -1. So this is 0. Magnetic spin. Is the electron we're talking about facing up or down? Down. -1/2. The definitions of these quantum numbers are more wordy than it needs to be. At the end of the day, it's kind of easier to see after you just draw the orbital diagram. You can add pieces together. Just take some practice. Let's do nickel. So nickel is 3d8. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Take a second and see if you can come up with the 4 quantum numbers for that last electron. Okay. Someone tell me what you got. Good. Principal quantum number, 3, because it's energy level 3. Secondary quantum number, subshell type. This is a D, and D is coded to be a 2. Orbital orientation. Which of these orbitals is it in? It's in the center. The center is 0. Spin, up or down? Down. Make sense, guys? Yeah? Okay, so we'll do barium. This will be the last one. So barium is 6s2. S's are easy, because if it's an S, you automatically know the middle two numbers are 0. Okay. And that's quantum numbers.